Hey, Dr. Clark coming back at you with another differential equations check your understanding video. We're in section 8.2, which means we are looking at homogeneous linear systems. And we've got one right here with initial conditions. They want us to write the system as a matrix vector initial value problem in Y, state space. Then they want us to find the eigenvalues and eigenvectors of the matrix and use that to find the solution, and then classify that equilibrium at 0, 0. If we have a homogeneous linear system, it's got to have an equilibrium at 0, 0, but what kind of equilibrium? That's the question. To do number A here, we're going to start with y, the state vector, to be xy. And since the differential equation is written as xy prime equals negative 2x minus 3y, 3x minus 2y, we can write that as d by dt of state vector y equals matrix negative 2, negative 3, 3, negative 2 times vector xy. Negative 2, negative 3 times xy gives you that negative 2x minus 3y. 3, negative 2 times xy gives you that 3x minus 2y there. But instead of thinking of that as xy, we're just going to write that as the state vector y. And then we've got initial condition y of 0 equals 8, 4. Initial condition given in the problem. So that's part A. We've written the linear system as a matrix vector problem. We're going to need to find the eigenvalues and eigenvectors of that matrix for part B. So remember, the part B, it's the determinant of the A minus lambda times identity matrix. And we usually write that as a determinant written this way: negative 2 minus lambda, negative 3, 3, and then negative 2 minus lambda. When we take the determinant, we multiply those diagonals. Negative 2 minus lambda times negative 2 minus lambda minus, negative 9, the other diagonal. So we go multiply, multiply, and subtract. Setting it equal to 0 gives us lambda squared plus 2 lambda plus 2 lambda plus 4 plus 9, or in other words, lambda squared plus 4 lambda plus 13. Clearly that equation, that quadratic equation has complex roots. So we're going to use the quadratic formula to find those complex roots. We'll copy this down onto the next page here. And when we use the quadratic formula, we'll get lambda equals negative 4 plus or minus the square root of 16, that's 4 squared, minus 4 times a times c, well, that's 52, 4 times 13, all divided by 2a, better known as negative 4 plus or minus root negative 36 over 2. Root 36 negative is 6i. So lambda is negative 4 plus or minus 6i over 2, or negative 2 plus or minus 3i. We have two roots there, but because we're just using the roots in order to solve a linear system, we only need one of the roots, and we'll construct the solution therefrom. We'll see that in a moment. So let's just take negative 2 plus 3i. We only need one root. That root will do. What is the eigenvector? Well, again, the eigenvector is matrix A times vector equals lambda times vector. The matrix is negative 2, negative 3, 3, negative 2. We'll use xy as that vector, and we'll take negative 2 plus 3i as that lambda multiplied by xy. So we're just using the definition of an eigenvector eigenvalue pair here. I'm just going to take the top row. Okay, what do I mean by the top row? xy times negative 2, negative 3 gives me the top row. That's negative 2x minus 3y. That's the top row here. And the top row here is negative 2 plus 3i multiplied by x. This is matrix vector multiplication. This is number times vector multiplication. So I'm just taking the top row, very important, top row. That's negative 2x plus 3ix. Very easy to make a mistake here. I'm just taking the top row, so I have x there multiplied by negative 2 plus 3i. This simplifies if I add 2x to both sides as follows. Negative 3y equals 3i times x, or in other words, y would equal negative I times x. So I just need an x and a y pair where the y coordinate is negative I times the x. And one idea would be to take x equal to 1 and then y would be negative I. That's one option. But then I have a minus sign. So I'm going to be a little bit clever and set x equal to I and then y will equal 1, because if x is equal to I, negative I times I would be negative I squared, which in other words is 1. So that's the vector we're going to use, but this one would work perfectly fine. In fact, any vector would work as long as it solves this equation right here. If you had used the bottom row, you could solve the problem that way as well, but you only need one row because they're algebraically equivalent. All right, so let's move on then. We can construct a complex solution from this. Complex solution is e to the lambda t times eigenvector, but lambda is negative 2 plus 3i, so it is complex valued, and the vector I1, the eigenvector, is also complex valued. So this solution here is not a real number, it's a complex number. Euler's formula lets us multiply out this problem as follows. E to the it is cosine of t plus I sine of t. So e to the 3it would be cosine of 3t plus I sine of 3t. Again, multiplied by that eigenvector I1. What I want to do is I want to separate the real and imaginary parts of this problem. All right, so e to the negative 2t, that's a real number. Cosine of 3t multiplied by I is an imaginary number. So that's not real. But I sine of 3t times I will be real because I squared is negative 1. So I'm going to write down negative sine of 3t in this first matrix corresponding to the real part. Then I'm going to write I e to the minus 2t. So I'm going to take this cosine. When I multiply it by I, I'll get an I. And so I'll have a cosine of 3t here. So the top row is this times I, right? That times I, but the I part with the cosine is imaginary, so I write that here. And the I times I becomes real, so I write that one here with the minus sign. The e to the 2t is just multiplied by both. I do the same thing on the bottom. Cosine times 1 is just cosine, so that's cosine of 3t. And I sine of 3t times 1 is I sine of 3t. The I is already there, so I just write sine of 3t. And what I have done is I've constructed a complex valued solution. Now our problem's a real problem, so I don't want a complex valued solution. I want a real solution. And the real solution is, it turns out, if you just take the real part here, that is one solution. And if you just take the imaginary part here, that is also a solution. And since the real part is one solution, and the imaginary part is one solution, I actually have two solutions, which is enough to construct the general solution. I'm going to call it y of t. The general solution would be c1 e to the negative 2t times negative sine of 3t cosine of 3t. That is one solution. And a second linearly independent solution is C2 e to the negative 2t times cosine of 3t sine of 3t. We do not want the complex function. That's no good. We want a real function, but the complex function gives us the real answer. So we use the complex function to give us that real answer. And there it is right there. That's the general solution. If we plug in y of 0, we will get c1 times, e to the 0 is 1, sine of 0 is 0, cosine of 0 is 1. E to the 0 is 1, cosine of 0 is 1, sine of 0 is 0. That's 0 plugged into the general solution. I want the initial condition to equal, if I remember, 8, 4. Want that to equal 8, 4. And so I think I can just set C1 to be 4 and C2 to be 8. And so now I have solution to IVP is y of t equals 4 e to the negative 2t times negative sine of 3t cosine of 3t plus 8 e to the negative 2t cosine of 3t sine of 3t. That is the solution. That's the answer to part B, solution to initial value problem, right there. If you want to know what Wolfram alpha says, it tells you the same thing. It gives you that eigenvector or eigenvalue, negative 2 plus 3i, and that eigenvector i1, just as we had. So you can always use Wolfram alpha to give you those eigenvalues and eigenvectors if you're getting lost on some of this algebra steps up here, but you still need to construct the solution. The other thing is, for part C, they wanted to know what kind of equilibrium is at 0, 0. Well, if lambda was negative 2 plus 3i, we're going to get a spiral sink. And that means it's a stable equilibrium. 0, 0 is a stable equilibrium because you're going to spiral in towards 0, because that e to the negative 2t shrinks to 0, but the complex portion gives you sines and cosines, so you're spiraling around. You can see that here in that phase plane. If you start here at 8, 4, you spiral in towards 0. And you can see that vector field is circulating. If you just plug in various vectors, you can kind of see that it's going clockwise or counterclockwise here. All right, so we've got a spiral sink. It's a stable equilibrium at 0, 0, and you can see that from that eigenvalue being complex with a negative real part. All right, so hopefully you were able to get that problem right, and you're feeling pretty good. If not, you might want to do a few more practice problems to get a better handle on how to do complex eigenvalue, eigenvector problems with homogeneous linear systems. And we will see you in the next video.